What if I told you that everything we see, every star, planet, atom, and photon, makes up less than 5% of the universe? The rest is invisible. It doesn't shine, doesn't absorb light, and can't be seen directly, yet it shapes galaxies, bends space-time, and drives the expansion of the cosmos. Welcome to Dark Matter, Dark Energy, and Cosmological Simulations, one of the most mysterious and exciting frontiers of modern physics. You're watching the Learning Studio, and in today's episode from our physics playlist, we'll uncover how physicists and AI researchers are working together to model and understand the 95% of the universe that remains hidden. You can explore the entire physics playlist by clicking the link in the description below. This topic belongs to our section Space, Time, and Advanced Technologies, where physics meets computation to explore the deepest layers of reality. The invisible universe, what lies beyond the light? For centuries, astronomy focused on what we could see: stars, nebulae, and galaxies shining across the cosmic dark. But in the 20th century, something strange emerged from the data. When scientists studied how galaxies rotated, they found that visible matter simply wasn't enough to account for the gravitational pull holding them together. The stars were moving too fast, as if an unseen mass was keeping them bound. This invisible substance became known as dark matter, not because it's dark, but because it doesn't emit or absorb light at all. It interacts gravitationally, but not electromagnetically, meaning we can't see it, yet we can feel its pull everywhere. Today, we believe dark matter makes up about 27% of the universe's total energy content. It forms vast cosmic scaffolds, invisible webs of matter on which galaxies are built. But there's another, even stranger force at play. One that dominates everything. The mysterious force, dark energy. In 1998, astronomers studying distant supernovae made a discovery that shook physics to its core. The universe isn't just expanding, it's expanding faster and faster. That means something is pushing galaxies apart, an unseen, repulsive energy woven into the very fabric of space-time. We call it dark energy, and it accounts for nearly 68% of the universe. No one knows exactly what it is. It could be the cosmological constant Einstein once proposed, a property of empty space itself. Or it might be a dynamic field that changes over time, a sign that our understanding of gravity is incomplete. Either way, dark energy is rewriting our picture of the cosmos, suggesting that the universe's ultimate fate may depend on the delicate balance between its pull and its push. Cosmological Simulations, recreating the universe. So how do we study a universe that's mostly invisible? We simulate it. Using the laws of physics, gravity, hydrodynamics, quantum fluctuations, and dark energy models, scientists build enormous cosmological simulations to recreate how the universe evolved from the Big Bang to today. These simulations are so complex that they require some of the most powerful supercomputers ever built, like Illustris, Millennium, and Eagle. They track the motion of billions of particles, modeling galaxies, dark matter halos, and large-scale cosmic structures that stretch across billions of light-years. But with simulations this massive, there's one challenge: the data is overwhelming. And this is where AI becomes essential. AI, the new lens on the dark universe. Modern cosmology produces petabytes of data, from telescope surveys like Euclid, Vera Rubin Observatory, and James Webb, to supercomputer simulations that model the entire cosmic web. AI and machine learning now play a central role in analyzing, compressing, and interpreting this data. Here's how. Neural networks identify dark matter distributions and galaxy clusters in massive sky surveys. Deep learning models simulate the evolution of the universe far faster than traditional physics codes. AI pattern recognition finds correlations between matter density, cosmic expansion, and dark energy models that humans might miss. AI doesn't replace physics, it amplifies it, helping scientists test thousands of theories, visualize cosmic evolution, and even predict where to look for the next big discovery. Some AI-driven simulations can now replicate an entire cosmic volume, 1 billion light-years across, in just minutes. It's not just computation, it's digital cosmology, the universe recreated through algorithms. Dark matter candidates, clues from the quantum world. Despite decades of research, we still don't know what dark matter is made of. But physics offers some compelling candidates. WIMPs, weakly interacting massive particles, heavier particles predicted by extensions of the Standard Model. Axions, hypothetical ultralight particles that could also solve other quantum puzzles. Sterile neutrinos, a ghostly type of neutrino that interacts even less than the ones we already know. Particle accelerators, underground detectors, and space observatories are all searching for these elusive particles, but so far, the universe keeps its secret. Here too, AI is accelerating discovery, filtering through experimental noise, identifying potential dark matter signals, and optimizing search algorithms for detectors like Xenon and Lux Zeppelin. The future, mapping the hidden universe. The next decade will mark a revolution in computational cosmology. AI-driven telescopes will scan deeper into space, while quantum simulations will explore how dark matter and energy shape the cosmic web. We may soon have detailed 3D maps of the invisible universe, not made of light, but of gravitational fingerprints. Physicists are already using AI-guided cosmological models to test new theories, from modified gravity to holographic universes, bringing us closer to a unified understanding of everything. And maybe, just maybe, one day we'll uncover the true nature of the 95% of reality that has always been just beyond our sight. Why it matters. Dark matter and dark energy challenge everything we think we know about physics. They remind us that the visible universe, the stars and galaxies we see, is only the surface of a much deeper, richer cosmic ocean. Through AI and cosmological simulations, we're not just observing the universe anymore, we're rebuilding it, pixel by pixel, equation by equation, in search of the truth hidden in the dark. Because in physics, the greatest mysteries often lie not in what we see, but in what we cannot. This is the Learning Studio, and this was our episode on dark matter, dark energy, and cosmological simulations. If you loved exploring the hidden side of the cosmos, make sure to like, subscribe, and check out our physics playlist linked below. In our next episode, we'll dive into cosmological simulations and the digital universe, where scientists recreate the birth, evolution, and structure of everything that exists. Because the more we understand the darkness, the closer we come to seeing the true light of the universe.